Hello everyone, my name is Federico. Today we will be starting an endeavor which will bring us to very high dimensional space, and we will be flying through these vector spaces and really kind of discovering some cool stuff which other people have come up with, but nevertheless cool stuff. Now maybe a little introduction. My name, I'll say it again because I guess it's Federico, and I am a undergraduate researcher at S2 Lab at King's College London, and I've been kind of doing it for a couple of years now. And my main area of thinking is or of research, I guess, is machine learning security, which is quite fascinating new field, or relatively new, and today we will be discussing this paper because I've noticed that maybe it could improve my explanation skills. So hopefully I'll be making a lot of videos on, I guess, machine learning security, and hopefully it will improve my explanation and my understanding of the topic. Because as the great Feynman said, you have, well, I mean, he didn't, I guess, say it, or maybe he did, but like, if you can explain it, if you can explain something, then you probably understand it. At least if you can explain it in simple terms. Cool. Today we discuss a paper by Goodfellow from 2015 ICLR. Now, for those of you who don't know, Goodfellow, I mean, I'm sure everyone is familiar with Goodfellow. He's the creator of generative adversarial networks. Legend says he was having a pint with friends and he came up with the GANs, which is quite a pint, I would say. And it turns out that Professor Goodfellow is actually quite a busy person, and he has a lot of good ideas, and a lot of them are in machine learning security. GANs and adversarial examples, although they share generative adversarial networks and adversarial examples, although they share one noun, they have nothing to do with each other. And let's start with maybe an introduction to adversarial examples. This video will be quite short. It won't go through the entire paper, just the introduction, like up to section 3, I guess, maybe 4. And then maybe I'll make a second video for this because this will just be too long. Cool. Let's say we have a classifier f parameterized by some theta, right? So this is like a classical machine learning problem where we are learning this function where x lives in Rn and the y is like, it's some set, right? Like cats, dogs, whatever, like some labeled, some finite, some finite, I guess it's like equals, not in, and these are cats, dogs, and whatever, right? So we have a finite set of labels, and then we are working in this n-dimensional Euclidean vector space or whatever, where x is like a subspace, maybe not necessarily like a subspace, but like I guess a subspace. What could this look like? Let's say we learn a nonlinear function, and then this is a binary classification problem, and obviously cats are x's, dogs are circles, and then this is like a classical problem where we're learning this during training time. We're learning this and then evaluating our model, whatever. This is not what we're interested in. We're interested in actually fooling this classifier. Let's say I'm this very evil person, and I have this point in my hand. This point is I guess a representation of a picture of a dog. So here's my dog, Mike. There he is with a nice tail and happy face. Cool. I should probably never draw a dog again, but regardless, the idea here is that we have this picture of a dog, but we are really interested in making the classifier think that this picture of a dog is a cat. What we do geometrically is we take this picture, right? This is just a vector, right? And we perturb it. We perturb it in the direction such that it will be the same picture, more or less. Think this like the same picture, but then with like some noise around it, right? Obviously, the noise is calculated in such a way that this perturbation is optimal, right? In other words, let's say we have this picture of the dog is x, then this perturbation, we call it eta just to be consistent with the notation of the paper. What we have is x plus eta becomes our adversarial example, which they call x hat. And the idea here is that we can maybe decompose it. I'm not sure. I guess, yeah, this is what they do. This is their notation. The idea here is that we're trying to make this, we're trying to fool the classifier by making it think that this feature vector is something else by minimizing this perturbation. So in reality, what we're doing is we get this eta, and it's an optimization problem such that we minimize eta with a specific norm, right? Why do we want to minimize it? Because if we did not minimize it, we could just get like a feature vector here, but then we apply so much noise or like so many modifications that we kind of lose the semantic meaning of this initial picture, and that's quite suboptimal. We want to keep the semantic meaning of the picture, but fool the classifier. So another example maybe which makes more sense is, let's say we have a classifier which tries to classify between malware and goodware. We take a malware sample and we apply some perturbations eta such that it's classified as a goodware, but it still keeps its maliciousness. And now you can see immediately like, oh, so if we can compute this in a somewhat clever way, obviously it's much easier on images than on malware, because images you can kind of apply like random dots and like it will still keep the same semantic meaning more or less, especially if you do it kind of and then we'll show like an actual example of this, and it does happen to be true. It's much harder with malware and goodware, but there's a lot of papers on that. Maybe I'll go over some in the near future, which this is like shown to be quite a possibility and quite a dangerous one. So maybe let's go over the introduction here. So Szegedi, which I guess is the third author here, made a discovery. Several models are vulnerable to the adversarial examples, and then maybe we'll discuss a little bit later more about this. Why is this a possibility? And I guess this is the whole point of the paper in general. This paper explaining and harnessing adversarial examples. So I guess it's the whole point. And this is what we're saying. They misclassify examples that are only slightly different from correctly classified. So we're minimizing this eta, remember. The cause of these samples was a mystery, and it was suggested to be due to extreme nonlinearities. We I guess as the authors show that this is unnecessary. Linear behavior in high-dimensional spaces is sufficient. Wow, that's a pretty bold statement, and what it means is that I guess it's the concept of Occam's razor, where like we can explain this through some like really weird like behavior of like nonlinear behavior, but in reality we could just say that it's because it's the linearity by itself is sufficient, because we're working in high-dimensional space, and high-dimensional space is actually quite hard for us to kind of wrap our hands around. And yeah, so there's some related work, and then this quite simple BFGS, which is like a kind of a simple, I guess, a quasi-Newtonian method, I think it's called, to find, like, it's a simple optimization technique, can find them already. Here the main contribution, well, one of the contributions is that they kind of come up with a very smart algorithm to do it, which is very elegant in my opinion. We'll go over it. Now, the idea here is that, and then maybe let's discuss it. This section here is possibly a hint to something which actually there's a lot of work done now in, and this is something known as robustness. And then I'm not sure if in 2015 this concept of robustness was like a formalized thing, but this is actually quite interesting. So the idea is that digital images often only use 8 bits per pixel, so they can only hold 256 bits, or like it goes from 0 to 255, right? So it's like there's only 256 possibilities. However, these networks are obviously, or like these models are still sensitive to precision, to modifications which are under this value, and this is kind of, I mean, obvious, but it has some very deep meaning. What it's saying is that these models don't really have any idea of what's going on, right? And they will still be sensitive to stuff like this. So in other words, if we take again this adversarial sample, maybe I'll write it up here to have more space later. If we take this adversarial sample x plus n, right? If we take the max norm of this perturbation, if this is under this epsilon value, then it really shouldn't affect the decision of the network, right? Because what we're doing is, effectively what we're saying is, if we take a point and we construct a ball which is less, well, with radius, let's say it's an open ball, right? If we construct an open ball with respect to a point x of length epsilon, now everything in this ball should have the same classification. But this is not the case, right? Because it's very hard to kind of give these semantic meaning, these semantics to these networks or these classifiers. Anyway, that's just one cool thing about robustness. What we would say is that it's not very robust, right? And then there's, maybe we could go over a paper on robustness, which they're very interesting. Now here we talk about dot products. Dot products are kind of fundamental to neural networks, right? Like, let's say we have a network with inputs and then like the hidden layers and then the output. Each kind of connection is just a dot product, maybe with a bias, but what we're really interested in is the dot product, because the dot product is in a function of the feature vector, right, of the input. So what we're saying here is we can split this adversarial sample into the combination of the initial vector and then this perturbation. And this is what we're in control of. Maybe I'll highlight it in yellow. This is really what we're in control of. And this is what we can mess with. Now we can maximize this increase. So let's say we there's this max norm constraint. Now max norm constraint is a robustness technique, which what it says is we cannot make this input like really modify more than a lot, and like more than a specific value, or the norm at least has to be like bounded by above by specific value. And this is actually like a very this I guess leads to like something like Lipschitz continuity, where you want to have this, you want to bound this Lipschitz constant by above, because or else the network becomes too volatile to perturbations, to adversarial samples. And so what we can do is we define this perturbation to be the sign of this weight vector. Why? Because we're trying to maximize this dot product. So maybe let's decompose this. This sign function, let's say we have a positive, negative, 0, negative. This sign function, this is the weight vector, right? This sign function will send this weight vector to 1, 1, negative 1, 0, minus 1. So it's just saying this is the sign of these, right? And then if this weight vector has n rows, and the average magnitude of the element is m, then the activation will grow by epsilon mn, right? Where epsilon is like your parameter. And why is this? Because what you're doing is you're taking the dot product. Now, if you take the dot product of a positive value with 1, it would. I mean, let's do this, okay? Let's say this is positive with 1 is just going to be this number. Positive with 1 is going to be this number. Negative with minus 1 is going to. So what you're taking is the magnitude, right? You're pretty much taking the magnitude of this vector and then multiplying it by some epsilon. This way you can assure that this epsilon, that this quantity will always be bounded by above, by this, so that you can always abide to this max norm constraint. Maybe I'll highlight this in yellow. Without this norm constraint, you can kind of do whatever you want. And this is the main philosophy. Adversarial samples are actually very easy to compute until you start introducing constraints. And now the idea is that this max norm of this eta does not grow dimensionality, right? It only depends on like the numbers, right? But it will still be, I mean, you can assume actually that for a large vector, it will, for images, since images only range from 0 to 55, pretty much for large vectors, eta will remain fixed, right? Because it will just be like pretty much 255, let's say, if there's one black dot. But the change in activation caused by the perturbation of n grows linearly with n. What this means is it actually, as the dimensions grow, right, this perturbation becomes more and more significant, even though the maximum feature perturbation remains constant, or is kind of independent of the growth of this feature vector. And this is really cool. What it means is that it's kind of a natural consequence of high dimensional space that we have adversarial samples which are very close, because very close it's kind of like what they're saying, right? As you grow the dimensions, these, like, even though they're all individually small, they add up to a big number, right? And we can think of it as accidental steganography. Steganography is the art of, like, I don't know if it's an art, but like of hiding. Let's say you have like this, like, meant to be a face, right? But instead of drawing it like that, you have like ones and zeros, right? And then it kind of like does a face, right? Like you're hiding messages within, I guess, I don't know. You can maybe look it up. This explanation shows that simple linear models can have adversarial samples if there's enough dimensionality to work with. Cool. And now maybe here there's the most important image or most important image in definitely machine learning security. This is like a big image. Everyone knows about it. The linear view adversarial samples suggests a fast way of generating them, and then pretty much here they come up with this kind of way to generate them. So again, here, let's say maybe let's have a look a bit at what this is happening, right? And then I guess I'll end the video after this section, because I think that's enough to kind of take in. Let's say we have this point. Let me get a pencil here. Let's say we have this point x, and then this perturbation, and then this decision boundary. Now, intuitively, what we can do is we can compute the unit vector here. Let's say this is eta, right? And then this is like, let's say this is 0, 0, right? So what we're doing is we're taking x, right, plus eta, and this sends us here, where eta is like the optimal direction. Now, what we can do is this kind of forms a subspace, right, a linear subspace. We can kind of like ride along this subspace by a factor of epsilon here, and we can kind of give it as much potency as we want, as much this is like the ideal scenario where this is the optimal perturbation, and we can modify epsilon in a way that we reach here by minimizing it quite easily, right? So the whole trick is defining this. So let's say it's x plus epsilon, and then since we want to minimize, the idea is to minimize this quantity here, epsilon n. What we can do is pull out n. Epsilon. This will be like some norm epsilon, and then we still, this is becoming horrible, but what I'm saying is we can pull out this epsilon here so that it will be still some norm, but like what we're trying to do first is minimize this perturbation, this direction here. This is eta, this box, and then we just multiply by a scalar value, and then this gives us the direction. And what are they doing here? If we have this loss function, which is under some parameters and some, training set or whatever, some x and y's, we can write the gradient of this loss function, like the gradient of j. And what we do is, instead of going down the gradient, as in like in a gradient descent algorithm, we just go up the gradient. What we're doing is we're finding this direction eta where we maximize this loss function, and ideally what this gives us is this updated this updated vector x plus n, such that the function here, what you're doing is you're maximizing the loss of this, which means you're misclassifying it, right? And And this gradient here is actually quite easy to compute because we just use backpropagation, which is what we're doing with training. The idea is that, yes, you need to, if you have knowledge of the algorithm, then you can compute this quite easily. And there's actually been done a lot of work where you can actually, even if you don't have the specific model, what you can do, because you need the specific model to compute this gradient, what you could do instead is train a surrogate model, which will be close enough to the original model, such that they will be able to, you can compute these adversarial samples from it. Yeah. I think I'll stop here because I feel like we've gone over quite a lot, and I feel like this is a good introduction to adversarial samples. Then maybe we can go over some other bits of the paper. There's other papers I'm happy to review. Yeah, so hope you enjoyed it. Thank you for watching if anyone got this far, and have a good day.